during the release of version 8, essentially we introduced several functionality for graphs and networks. And the whole idea essentially was to put in place the background to actually be able to build stuff on top. And one of the first application or the first vertical for it is social network analysis. So what I will probably do is just to give you a brief idea of this set of features, which will be probably in the next coming version of Mathematica. So I give a brief background on network analysis and social science, give the practical application and some motivation why it's interesting for everyone to actually have an idea. And after that, I will probably make directly the link with Mathematica and show how you can represent a network in Mathematica. And then I will talk about a set of functionality or property to actually analyze the graph. For those who are actually in the earliest talk, as I point out, almost everything relies on the fact that you do modeling and then you do analysis, and simulation is in between. So the modeling part here, I will not even talk about it because we kind of went through that in earlier talks. So here it will be essentially the analysis, so the social network analysis. So, I will not spend my time in the history, but essentially the social network and the analysis just resolved from sociometrics, graph theory, and social network analysis. If you are interested, we can discuss about the story later, with different versions. So, essentially what you have is a network. By network, I mean a graph with a behavior, right? A graph, beside the topology of a graph, you actually assign a property, some behavior to your graph. So in this case, for example, this is the flow of email communication of the Enron organization. As you know, when they went bankrupt, there was a lot of lawsuits and people grabbed information. So this kind of this is just the email of people who send more than 600 emails to their friends or neighbors. The graph is actually huge, but I just represented a subset here. And what essentially people do is to take those networks, analyze them, and try to understand which people are most important in the network, which exchange more emails, and be able to do a decent analysis and see what actually happened. So another example, which is a standard one, is the Zachary Karate Club, which is actually one everybody use. It's essentially the friendship in a karate club, and actually people study it later more in details because there was after that a session in the whole club, and there were essentially two groups, and by analyzing studying the graph and looking at property, you can actually detect that by just looking at it. So I probably show some example where you can actually see the partition and how, if there is an issue in this sort of networks, how it will split. So just to give you an idea, there is several applications for social network analysis. So from computer science, where you study web pages, internet traffics, to information disseminations, several corporations do that, for efficiency and traffic. People use it also on business analysis to study the communication flow in an organization. If you have your organization and you want to improve it, and see how the workflow goes. One application I will actually illustrate is actually what the law enforcement and all the intelligence agencies currently do is they use clique and other cohesive groups to actually be able to identify criminal and terrorist network. And it's a quite useful tool they actually currently use. And I will probably also talk or show some example, and that will be probably in tomorrow's talk on the graph data mining, how you can actually extract and connect to Facebook, extract the network of your friend or friend of friend, and analyze it and have an idea. And there's more applications. So let's just go directly in more useful things. I will not stop. I will not continue the motivations. So as I said before, for a network is a graph where you actually add some property. So it's something real. It's not just the topology. It's not just the relation between entities. So if you do, for example, you're in physics, the phase transition, actually a lot of results, for social network analysis are coming from physics. Phase transition are a nice model for networks. In sociology, the social interaction and ties among actors actually are networks. And that's actually the topic where we're actually going to focus today is, the social interaction between peoples. Down here, I just have a tiny view of, the web. This is just the Wolfram site. I just wrote a tiny crawler, and, you kind of see the network. So now let's see how you represent actually a network in Mathematica. So a network is essentially in Mathematica a graph, right? And a graph where you associate some property, some object on top. So this is an example. You can build, an undirected graph and query that is an undirected graph, or you can construct it from an adjacency matrix. So essentially, we have several ways to construct graph actually in Mathematica. So you can actually just use them to construct actually a network. So up to the difference that, the object in our head, we call it graphs or network graphs. So let's look at some main property, you have. One of the main property in social network people, analyze or study is homophily, where it's essentially the tendency for people with similar character to associate, themselves. Like all of us here, we have something in common. We all somehow use Mathematica or like it or dislike it, but that's why we are at the conference. So that's a similar characteristic. So if you go, for example, you take a network of students in high school, for example, you can look at the interaction, do they associate themselves, based on the age, the race, I don't know, the level in school where they are, or some other characteristic. So what people in social network try to do is actually to give a quantitative measure to that. And what they do in this case, or they define in this case, is what they call associativity or modularity. It's actually just a measure to actually see how people of the same type relate or associate themselves. So in this case, is an example of the Zachary Karate Club I earlier taught. I actually showed. You can take that graph and just partition it. So based on some parameters, so I just pick them appropriately. And then you can highlight them. So all these functions I'm using are actually available in version 8, plus or minus a couple of them which are in version 9. So from doing the partition and you look, you see that you actually have two groups now, which are nicely split, and then you see the connection between them. So, and you can compute the modularity of that partition and see that, in case, how people of that group, from those two groups associate themselves. So if the modularity is a value between 0 and 1, so if the value is great, is close to 1, then people of the same type associate themselves. And if it's close to 1, minus 1 also depending on the normalization, they are actually dislike. So as I said, so if you compute then the associativity, it gives you 0.67. So they are kind of similar. So people of the same type or the same level of connectivity associate themselves in this network. So this is, associativity is actually a measure to see how people of the same type associate themselves too. So the other example I want to talk about is transitivity and cliques. So clique is actually a subgroup which is fully connected, or you can look at it as a cluster of fully connected, people. And transitivity is essentially what you usually think about in mathematics. If A and B are connected and B and C are connected, then A is connected to C, essentially. So these two properties, when you bring them together, actually are kind of crucial and important, characteristic of networks. So this is a data of actually what several intelligence agencies actually collected after the 1998 bombing of the US embassy, I think, in Africa. So this network, is just a network of communication, so they have no idea, but from there they want to actually be able to isolate cells, terrorist cells, and actually even be able to predict which are the one will be active and actually, did the attack. So, I just hide the data. So this is actually just the data. the people, the edges. This is the graph. And here I compute find click. So as you may notice, this is just red because actually it's a new extension of what we'll have in version 9 of find click. People requested some new functionality and which are quite useful. So this one actually kind of look at the graph and compute the click, or compute all possible click you can find of size 5. And the result is just displayed down here. So as you see in this network, so I hope it's visible, you have the click here, which is in red, and the second click, which is here. And from the information actually they got, this is the set of people who actually conducted the attack. The first one, I believe it was in Kenya, and the second one here. So you see that all those people which are actually involved directly were actually contained in the click. And it's what actually people are actually currently using, if they have communication between terrorists or such, actually analyzing them, analyzing that. And the bank also are doing the same, to actually be able to analyze transaction, figuring you actually make, fake transaction and such. So there's a whole set of people actually now using network analysis. So let's look at other metrics. So there is a set of metrics actually also people are using. They call it centrality metric, centrality measure. So those metrics actually provide you some information about your network. So in this case, it's just the degree centrality. We just give the degree of every node. What's important with the degree centrality is that it's actually useful to actually know which are the important node or the central node, and how the central node with respect to how the information is spread in that network. So for example, this is a network of retweet on Twitters. So who retweet to who, so it's a directed network. And you see that, for example, this node is the most important one. So if you are a friend to this guy, and you tweet something and you want other people to actually get that information, that's the guy to talk to. So he can retweet your previous tweet. So probably tomorrow in the talk, I will show you actually how you can actually, from Mathematica, tap in Twitter and get those data informations. So the next example here is is related to the Britishness centrality. One usual question people always ask is in the Renaissance, in the Italian Renaissance, where people find out that the Medici families kind of end up to be important and quite influential in the whole structure. People actually try to understand why, because they were not the richest one, they were not the most influential one in terms of politics. But it happened that, even now, when you read the literature or the history, they are the most important family, as the most known ones. And essentially, what people who study social science did is they look at the Florentine family marriage. So all those rich family are important one, how who marry who, and the whole relations. And if you look at the Britishness centrality, which essentially compute the shortest path. So the claim is essentially that the Medici family was able to actually break a lot of deals through the marriage. So they were married, they married the daughter or the nephew of somebody else, so they have a lot of connection directly to the family. And so one way to actually prove that is to use the Britishness centrality. And here actually kind of highlights the degree, the Britishness for each family. And you see that the Medici family is actually in the center. So if you want to break a deal with this family, you have to go to them. So it's actually where the influence was coming from. So this is actually kind of one way to actually see how network analysis and social science can be used to aid other areas, like in history, to actually prove a fact. So the next example is the closeness centrality. So in this case, it's just an example of an epidemic network. So I just generate an epidemic network from the degree centrality. So the closeness centrality is actually an important, an important measure to see how you can, the speed of information dissemination. So this is an example of a disease network. Like you have the SARS in the couple of years ago, which started in Asia. So if you want to actually control it and you actually have the network of people, how the contact, who is in contact with who, you can actually just compute the closest centrality and know, which are the people you have to isolate, because they are the most important one which have connection with people. So I will go slightly fast. So the last example I have here is the eigenvector centrality. So the eigenvector centrality is kind of, roughly speaking, is the weight of sum of centrality of the neighbor. So if you know how someone is, if you know the weight of the neighbor, you can compute the average sum, and then provide it to, compute it and get the the eigenvector centrality. So this centrality essentially just show who is well connected. As you all know, it's good to be connected to somebody important, so you're important. So again, the eigenvector centrality actually just compute that. So in this case, for example, we take the collaboration network. It's a citation network, roughly speaking, who collaborated with who, and then we want to find the author that have the most citation or the most important citations. So you can just compute the eigenvector centrality, and then you find which node in your network, in that astrophysics network, actually collaborate or well cited by other people. So I will go straight to the structure of network, which is another aspect in social network analysis. So essentially, when you have a network, you actually want to know if your relations are reciprocal. As usual, we always think that friendship is a symmetric relation, which unfortunately people actually check. It doesn't appear to be the case. So if you run a survey, you figure out that actually the person you think is your friend will not check that is your friend. So one important measure people introduce is the reciprocity, which actually just a fraction of the number of relations which are reciprocal. So this is also a new function in version 9, or will be in version 9, hopefully. And it kind of gives you a value between 0 and 1. So if you are 1, that means your graph is fully bidirectional, so it's symmetric. So here is just an example for the high energy physics article, set of articles, citation network, and then you can see actually how the collaboration goes and who cite other paper. And you can guess that for a citation network, for sure the reciprocity should be low, because paper don't cite it. There's no reciprocal relation between people who cite each other once. So the other important measure is the density, which is roughly speaking similar to what you have the density for a sparse array or for a matrix. So essentially here you want to see how well connected your network is. So it's again a measure between 0 and 1. So in this case, I just look at the Zachary Karate Club you had earlier. I compute the graph density, and I see that actually is not so well connected. And people use this measure in several other cases. Like for example, you can look at the transportation network or communication network, compute the density. Besides looking at the connectivity or other codes and such, this can also already give you an idea of how strong or robust a network can be. So another property is the clustering. So it's how many different communities you can have in a network. So this example is just a plot for the Watts-Strogars distribution. So Watts and Strogars in the late 1990s actually introduced this random graph distribution to essentially simulate small world. They built it just because they were inspired by the 6-degree separation. You all know the Kevin-Bacon network. So they were trying to actually find a model to actually be able to simulate and produce several of them. So they introduced actually the Watts-Strogars distribution we have in version 8. And essentially the way it's built is essentially a circle where you have connected people, like in a circle you have more connections, circle have 2 connections, you have maybe K connection to the next one. And you randomly pick an edge and then connect it randomly to another vertex. So you can switch the endpoint. So that gives you a network which have a high clustering degree. So that means there is less less community, because you kind of randomly switch them around. And the shortest path is really small, which is also one information they needed, one attribute they needed. So I will just jump this, which is the average and the longest path. So this is a function in Mathematica. Graph diameter, which gave you the maximal length of the longest path, and the mean graph distance, which give you the average. And I kind of just talked about it earlier. So this is the one simulation of the Wastrogas distributions. So it's really dense and connected. And as you see, you have a good mean clustering degree. So in version 8, we'll have several clustering functionality, local, mean, global clustering. So there is several variants of the clustering coefficient. And the other network, which also appear now, which is actually nice to simulate the internet, for example, or the web, is a preferential attachment network, which was introduced by Barabasi. Albert and Barabasi actually both. And is actually essentially that, if you look at the degree distribution of vertices in that network, they have a long tail. So it's essentially the power law, like illustrated here. So people usually use this to actually simulate network and analyze them. So just to conclude and not go further, social network is quite important. What I mean, we are all connected. We are all using Twitter, Facebook, and sometimes it's actually useful to actually look at quantitatively the information you get from there. If you look at your LinkedIn, and if you are looking for a job, who are the most important people in that network you should actually contact. You don't randomly just open it and send email to people. So there are measures, well known, which actually provide you those informations. And that's pretty much it. Thank you.